Hi. So this is the lesson on data standardization, and it's a very short introduction with an emphasis on the incentives and the reason why we should think about data standardization. So some motivation, what does it mean? How do we do it? And a quick couple of conclusions. Motivation, I think we all know the problem of the small ends. If we have more data, we have more ways of getting solid results in neuroimaging in general, but also in general. And that's the number of subjects that were used in in studies as a function of time of publication here. And you see that in 2015, we were at about 20-ish. And we are now something like between around 25, 30. And that means that we have only power for a small big effect sizes. So in 2015, it was about effect size of 1. I think now it's about 0.7, 0.75. But still, we do need to increase our sample size. And that's the samples, the effect size that we get in the HCP dataset. And that means that we have a still very low power using our standard neuroimaging sample size. There's another aspect to it, which is more on the generalizability. And you know, when you take only a few subjects, and if you train on that small sample size, you're also likely to have like a sample size that is a cohort that is very homogeneous. So if you start to train or to do some statistic on either, let's say, a younger cohort or an older cohort, but you test or you want to actually do results on the old cohorts, or the opposite, or you train on the old and you want results on the young, on the old, this actually impacts quite strongly sometimes the machine learning prediction that you can do on dataset. And therefore, really, the need for large dataset is not only for the classical statistics, but also for the machine learning, obviously for the machine learning applications. And in general, we have quite a few large datasets, but there's still the minority in terms of the number of data sets with big and large organized data. UKB, for instance, is one of the classical examples, ABCD, all those large cohorts and consortium. However, the number of small little data sets being produced around the world is absolutely enormous. It has been assessed as you know, like costing us billions of dollars of acquisition. I don't know if the number is correct, but at least the idea is correct that we are indeed acquiring a lot of small data sets that are not reused. So reproducibility caused by issues in data is a natural thing, and it's less rarer. It's less rare than what one may think. So I just point to a couple of issues. One thing is that the license of the data is maybe not amenable to reuse. The database that you're using does not always contain the right information that you think it has been checked, but it hasn't. The QC is not necessarily reliable. There's a whole bunch of imaging data, a whole bunch of issues with potential header problems or orientation problems. The provenance of the data is often very poorly documented, and so on and so on. I really love this little YouTube video. I've put the link in the slides. You should take those 3 or 4 minutes to listen to that. And you know, and certainly the raw data and the original data that cause of problem. You know, I'm just taking that tweet from the Free Surfer HCP people that say, hey, we've pre-processed data with that version of FreeSurfer. Please don't use the release data. We found an issue with those with that release and so on. So how many issues actually have not been detected is the question that we should ask ourselves. So what does standardization mean and provide and provides? So first of all, I would like to establish 3 layers of standardization, and I'm going to use standardization and harmonization in the same way here, but there are subtleties. The first layer is the format and unit. So in the case where the information is really the same, do we have a standard way of describing that information? So for instance, the format, is the format the same? So we have exactly the same information, like in your image, for instance, and some of it is maybe in DICOM, some of it is can be pushed in Nifty, or we have the edge, but the edge is measured in month, or we have the temperature, it's measured in Fahrenheit or Celsius. But those things, if we have exactly, I know that there are lots of information of sometimes a bug introduced in when you're going from one format to the other, but let's say that in general, formats and units are a solvable problem as soon as we have a translator that goes from one format or one unit to another. That layer, though, is already a problem when you're trying to kind of get data from different sources and reuse data from different sources. So finding and using the most common and the most established and the one established in your community format and unit is absolutely critical as soon as you start to have a need for reusing or sharing data. Then there are, I would say, easily mappable measured and versions. So for instance, there is a UDPRS or a test, a specific test that has been done on a population of subjects, or maybe let's say it's a MOCA test, or it's a some test, and maybe this one is done in French and this one is done in English. It's really the same translation, and really is the same information. There might be subtleties and things like that, but there are really mappable measures. You can maybe there's a little bit of a re-standardization to be done across the columns, but it can be taken as the measure of the same thing. Okay. And then there are related things. Let's say I have, I want to measure some anxiety level, and I've got a first test that measures some of the anxiety level, and then in another research group there's another test, test B, that measures also the anxiety level. Test A and test B are not the same. They aim to measure the same construct on the same thing in subjects, but they are not the same. It's unclear unless you have studied specifically the relation between those two tests, and it's quite hard and sometimes really impossible to do. It's not clear, how you can map exactly those two things. However, they both measure anxiety, at least they are supposed to. So they are relatable and mappable in some ways. And there's a lot of work to know how you map those things, and is it feasible or not, and so on. So the standardization benefit from a number of point of view, and what's important here in that slide is that you would like to know that this thing is related to anxiety, or you would like to know that those two things are very easily mappable, and that's that the information, that standard description of things is where things are important to be able to do that. So a number of use cases. So I need to expand my training samples. I want to grab data from elsewhere. How do we integrate data? Where do I find data of Parkinson patients that have completed the MOCA? That sort kind of query requires standardization of information and metadata if you want to be able to do that. Or even like, in your own institution, what data do our PIs have? How can we advertise our data without sharing the data and so on? So that also standardization is really important for that those use cases. And if we had the Google power on data sets, we would be in a different situation in most research fields that we are in the moment. So I just want to have the briefest introduction to linked data. So I've called it linked data 0.101, which is basically linked data was basically invented with the web, with the World Wide Web. Where the first stage was to actually abstract the location of documents with their physical in their physical machines. So you wouldn't care whether the document is on one machine or the other. You just care that the document you can read the document and link to it. Then there will be services and companies that actually build on the top of that principle to provide services, right? So all those Facebooks and we're able to actually produce content. And then the last step, which is more like the semantic aspect, is that you can actually attribute meaning to data. So linked facts and facts with meanings rather than documents. So at the stage where possibly in the future, you can let a machine reason on the data available on the World Wide Web. So those are the linked data, kind of a very, very basic things. And often the format, that is represented is in the form of a graph where they have some triplets where, for instance, the entity Bob as his relation, which is a, and then person is another term, and so on. And Bob also has a friend, and then Alice, and so on. And so you can build those triplets and create a graph on which you possibly can link data across many steps, and many steps, and then query that graph for as long as the terminology and the predicates are known and if they are standard, they will be like a much powerful way of querying, of course. What's important also to realize is that that standardization, even in key aspect, for instance, coming back to what Sebastian took for like an example in that presentation, is the Vioxx scandal, where a drug was possibly, was actually increasing the risk of stroke, and the FDA had no way of actually knowing that because data were not harmonized across country on those things, and it was impossible to know the effect. So maybe stroke was not coded the same way, or what kind of stroke was not recorded, and so on and so on. So they invented through OMAP. They invented they basically started to say, hey, we need to record exactly in the same way with the same vocabulary, with the same terminology, and have a common transformation to a common data model, such that we can do the analysis of the data and eventually know whether that drug is harmful or creates a risk for a specific disease. And that's what is the effort of OMAP and SNOMED City on those. Here in this instance, we like 120 million people were actually recorded in that example. So how do we do it practically in our research and things like that? So I want to start with the obligatory, mandatory kind of a cartoon with the final.doc document where the PhD student is painfully trying to get the final version of that document, and it's usually an example that is used for version control. Actually, docx document don't go well with version control, but what this thing means is that the organization on the disk and the file name on the disk on the support layer, on the physical layer where you're going to store data really matters. Is going to be impossible to know what is the latest version if you don't have metadata such as date and size and all those things, just by the name of that document. Format is absolutely critical. So why does it matter? Because some formats are actually proprietary or amenable to version control or not, or are kind of standard to a community. So Excel spreadsheet of docx are standard to a very large community. However, they have their problems in terms of again version control and also possibly proprietary aspects. So you have to check whether that format in a few years' time is not going to be behind some kind of paywall, or not all the tools will have the capacity to read that format. So PDF is kind of standard, but it's some tools can't read all the PDFs. So the less proprietary and the less complex the format is, the more likely this is going to be easy to use. License, copyrights, and support and long-term support and all those, and obviously availability for reading those formats and those are the questions you should be asking yourself before starting to put data in a specific format, even for text. So I would definitely recommend, like, as long as you can do Markdown, do Markdown. If you really have to do docx, then you can go to the docx and so on, because of the simplicity and perennity somehow of the data. An ASCII file is not going to go away, and every computer is going to be able to read an ASCII file, even in 50 years time. I mean, right, the docx version that you're using today, we don't know when it's going to change and when the tool is going to not be able to read that. Where we store data is also critical. Please look at the governance of the platform where you're putting the data. I'm putting things on Google Drive, and when is Google is going to make me pay for that? They decide those things. I haven't signed a contract with Google, so they might change their way of doing things. What is the security? I mean, how much of those things there are mined by Google? So basically, there's no free lunch. If you're using a tool that is a free tool, unless you're actually building this tool yourself, like you have your own SSH server or you have your own things, then most often than not, there's going to be a cost associated in some ways that is not obvious. Look for the governance, license, cost issues before using any platform to share data. So in neuroimaging, we talked a lot about standards. I would have a quick go at the bit standards and before the next session, the next recording, look a bit like foreshadow the NIDM model, and maybe give you an example of how those things can be used. And the first questions, what is BIT? So the brain imaging data structure has been proposed in the neuroimaging community to standardize the way we organize our neuroimaging on the disk. And to some extent, it can be a little bit of a painful process to actually put your data in bits. And the reason why you should do it is really to make sure to first of all yourself in the future know what those data are and how to and have the metadata associated with those data right with the data set, and be able to actually come back to data that you may have entirely forgotten how they were acquired and what they were about, and and all those things. So BIT is really kind of your like a notebook associated with the data, embedded in those data, such that you can share those things in a standard way and reuse things yourself and others in the future. How much do I suffer in the process? It can be a little bit painful. There are bits have some mandatory fields and mandatory things that they're asking you to do. There are also a lot of recommendations that are not mandatory, but they sometimes very important recommendations. So once those data are in bits, maybe the most prominent example is neuro, where there are 300 data sets that can be shared and easily understood because they share the same data structure and the same file name structure. What bit does is it adds specific little files that say, hey, those are the column names, but they are not specifically standardized at the term of the common names. So that's a problem that can be solved with other tools. There are variable values and in those TSV or CSV files, and there are files that kind of describe things more in depth. So what does that term mean? What if those files themselves are not really standardized? So it's more like an individual journey how to create those things and how to reuse those things. But at least there's like a sort of a way, or that sidecar JSON file will describe the associated data, or the participant.tsv file will describe the participant, the cohort, and so on. So it's not easy to actually recreate a dataset from several datasets when you're having bits data, but that's a layer that we can add with future tools, and my colleague Dave Kennedy will probably talk much more in depth about that. So, bits take, for instance, DICOM directory with lots of DICOM files, and there are many of those files, and that's it can be an issue, and creates a specific structure on the disk with per subject. You have like the modalities, and there within the modalities you have the images, and the names of those images actually have a specific structure themselves, so you can easily move those files and still maintain the information while moving. So here, for instance, you got in the functional one, you've got sub 01, meaning the subject with the identifier 01, and then there's a sequence of key value pairs that are, for instance, so key is here sub, for instance, for subject, and 01 the value, and then task is the second key, and then rest is the value, and so on, and then underscore a last information about the type of data that you're dealing with, plus the associated JSON file if needed. And that's the basic of bits. It has all those nice structure where you actually find the information and the metadata more easily. So this is an example of JSON sidecar file where the name ADHD has a description, and it has a description of what are the levels, and 1 means yes, and 2 means no, and so on and so on. So that's those JSON sidecar files can be completely critical to understand the values in the for instance in the participant TSV file. So the TSV file itself, the participant has participant ID, gender, age, handedness, and then a number of variables that are there or not. And if they are, they're not. They should have a JSON sidecar file to make sure that you understand what those things mean, because it's not, and maybe it could be unclear what is the some of those things. QC REST 1 is, what does it mean? Again, it's something. Sometimes it's obvious and already standardized, but in general, it is not. So yeah, this is just another example of sidecar file associated, so where handedness is described and verbal IQ is described, and so on and so on. So let's say that you have all those metadata information. There is the possibility to actually query across data sets now, if with those information, by having an integration of a metadata layer, where if those metadata are standardized or harmonized across data sets. And this is an example of what the NeuroBagel team did with Sebastian, Jonathan, Norman, and so on, and others at McGill in my lab, and they look at the bits data set. They standardize those things, those values, those columns with specific pointers to a URI that says, hey, this is exactly what I mean. I have the definition. If I click on that link, I will see the definition of what that term is. And that allows you to actually think of a very large and distributed data management, a possible data management aspect. I also want, let's say, for coming back to this, once all those metadata are standardized and well described, then we can start to build the tools to actually query those things in a reasonable manner. I also want to point you to one specific, very important project that is reusing the basic of version control for datasets, and that's the DataLad project. It is a very large and very important and very powerful project, also with its complexity sometimes of usage, although the team is doing really its best to minimize those complexities and give a tool that is available for like a large community. But it's a very important tool that I would really recommend that you check out and listen to the tutorials. There are many on the web. And there's a DataLad handbook to guide you to the usage of that tool, which is a really distributed data management and version control that helps you keep track, create a structure of your data and derive data, also considering the pipelines and help you collaborate across the globe. These are just a few of the people that I should thank for this video, and I thank you for your attention.